All right. So,
Cool. Hey, everyone. I just want to introduce these two folks. So today, because of the Omicron variant and not wanting to hold things in person, I thought it would be an excellent opportunity to have some guest speakers today. So it's Shashank and Shishir Dholakia, who are, their last names are just coincidence. They're unrelated. Uh, that's a joke. And they are recent Berkeley graduates. So they just recently, they were undergraduates, but they're graduating this winter. And they'll be here to talk to us about exoplanets. And yeah, I guess y'all can get started.
Sure. Yeah. So thank you for that. Yeah, so we'll be talking about like our paper and then
roughly stars and exoplanets.
Yeah. And so it's called like efficient and precise transit light curve for rapidly rotating oblate stars.
To start off, I want to get a sense of what all of the subfields of the participants are, just to get an idea, because I know Nicholas, but I don't think I know what the subfields of everyone else is. So maybe if you want to say in the chat what your interested subfields are, that would be great. Gravitational waves. Okay.
Also, this is like going to be really informal, and like we're going to be like interjecting for each other. So also, you guys feel free to interject and ask any questions if you have them while we're going through. Okay.
Okay. Interesting.
So
a lot of numerical relativity. So this talk will be quite far afield, I think, of numerical relativity, but I am going to try to argue for why I think it should be interesting in general for people who are interested in stars and planets and using that to test models about stars and planets.
Yeah. So yeah, so I'm obviously from the exoplanet field. I mainly focus on like detection and characterization of exoplanets. And I know that in the exoplanet field, there's like a common adage, which is know thy star, know thy planet. And like I would argue the reverse is also true. Know thy planet, know thy star. And so stars and planets are very inextricably linked to each other, and understanding one is essential to understand the other. And a lot of this paper is, in my opinion, important because it's like a way to use planets to leverage planets in order to understand the stars, and also to leverage stars in order to understand the planets.
Yeah, and for me, I think like the one thing that I want you all to take away from this journal club talk is essentially the importance of photometry. So I think as astronomy is heading more and more in a direction with JWST and stuff of collecting a lot of light, photometry is becoming more and more important. But specifically, I think it's really important for people to be able to model actual astronomical objects and try to understand what the integrated light output from those objects are, and go back and forth between the photometry and the actual physical object in space. So this paper, in my view, is one way of doing that. And I hope that this essentially continues. So
yeah, and so yeah, I was talking about exoplanets earlier. Some context about the field. The first exoplanet was discovered in I think the 90s or so, and the first exoplanet discovered through photometry was discovered in the 90s as well, and ever since then, there's been an explosion of planets found through this particular method, the transit method. The Kepler Space Telescope, launched in like 2008, I think, has discovered thousands of exoplanets. I think the count is upwards, almost 4,000 confirmed exoplanets, many, many more candidates. And nowadays, there's also the TESS spacecraft, which is setting out to find planets around stars all over the sky. And one of the things that these spacecrafts have found very often are these really extreme and strange planets called hot Jupiters. These are like Jupiter-sized planets that orbit very, very close, sometimes with periods less than 10 days, right? And they are really, really anomalous. And one of the big things that we don't understand about hot Jupiters is how they actually form. So in planetary formation, you have like a star that forms and there's a circumstellar disk around the star, right? And we think that planets form within those circumstellar disks. The problem with hot Jupiters is that they are orbiting so close to their star that it's a bit of an enigma how they get to that point. They can't form there because there's literally no nucleation points. There's so much radiation from the star that close in that there's no nucleation point for material to start accreting around. So we think that the planet has to form beyond what's called the ice line, where like solid materials can form, like silicates and things like that. And those serve as the nucleation points that seed planetary growth. So the big question is, how does a Jupiter-sized planet form out there beyond the ice line and somehow get to the position that we observe them right now, which is like really, really close in, right? So there's two competing theories. There's disk migration, which is basically the circumstellar disk and various bodies within the circumstellar disk steal the angular momentum, the orbital angular momentum of the Jupiter-sized planet, right? And over time, it sort of pulls it in and it starts to orbit very close in, and then it tidally circularizes. So the orbit is very eccentric at first, but over a relatively short time scale, that orbit circularizes because it's so close into the star that the tidal effects are actually quite strong. The other possibility is planet-planet scattering. So this entails that the hot Jupiter forms in like in our solar system. There's a Jupiter and there's a Saturn. So typically another planet gets too close to the Jupiter-sized planet, and that planet is knocked out of the system, kicking the Jupiter-sized planet in, and then the Jupiter-sized planet then assumes a very eccentric orbit that then again circularizes. And so these are two competing theories of how hot Jupiters form, and we don't really know which one is the correct approach. But one thing that we do know is that every time we observe a hot Jupiter out there, we almost always find them in single star systems. And this is a really, really big enigma. And it hints something about their formation that we don't really understand, but it underlies like their formation process somehow. So understanding how they form is pretty crucial to understand why we always observe hot Jupiter systems in single planet systems, and we never observe hot Jupiters in multi-planet systems. Very rare. Yeah, very, very rarely. I think there's only like 1 or 2 cases out there. Right. Yeah, and so the most important way to measure this is through a parameter called the spin orbit angle, which is basically if the star is spinning in a particular direction, right, and the planet is orbiting in its own plane, what is the angle between the angular momentum vector of the star and the planet, right? And that's called the spin orbit angle. That basically gives you an idea of what is the dynamical history of the system. If there is some like early like gravitational violence that occurred in like a planet-planet scattering event, we expect the spin orbit angle to be large. We don't expect that the planet is orbiting the same plane as the stellar rotation, right? But if there's like a more like gentle disk migration going on, then we expect the spin orbit angle to be relatively low. And of course, in our solar system, we have a nice multi-planet system that's very well behaved. All of the spin orbit angles are very low of the planets, right? Under 6, I think around 6 degrees is the spin orbit alignment of the average planets in our solar system. Yeah. So broadly speaking, like our solar system has a very gentle dynamical history, but we suspect that hot Jupiters often don't have gentle dynamical histories. And a very, very important way to probe that is through this measurement of this parameter called the spin orbit angle. So essentially, a large part of this paper is in a new way to measure this spin orbit angle. But so that's where the know thy planet, know thy star comes, or know thy star, know thy planet comes. But it's also important to use planets in order to understand the stars, right? So I'm going to go down into the introduction, but essentially, I'm going to talk now about the stars part about this, and how stellar rotation works specifically. So, I mean, stars are balls of hot gas. They're in hydrostatic equilibrium, right? That's one of the tenets of what you learn when you learn about stars. I'm gonna share my screen. Hold on. What's going on? Oh yeah, it's gonna stop your screen share. No, that's good. There we go. So so let's get rid of this. So how many of you have taken like a stellar astro class? I'm going to assume that that you all have taken a class on stars in some capacity, and if you have, you've probably seen this this equation, which is the equation for hydrostatic equilibrium, which is something like so dp over dr is equal to gm rho over r squared, right? So this is the conceptual idea behind hydrostatic equilibrium is that there's a pressure gradient inside the star, which is supported by gravity. You have the pressure inside of the star is essentially balancing out the force of gravity, which is pulling it inwards, and some form of energy, which is holding the star out, right? Now, if I rearrange this equation, hold on. I can rearrange this equation in a neat way, which makes it much more amenable to describe stellar rotation. So the way I'll rearrange it is right. So this rearranging of the equation allows us to describe hydrostatic equilibrium in terms of the local surface gravity. So another way to say this is, or a more precise way to say this is this, where the gradient of pressure as in the star divided by the density, the local density in the star, is equal to the local surface gravity, essentially the G constant on the star, right? And that can be written in terms of two things. One is the familiar gravitational potential term, right, which is what you've all seen. But also there's an additional term which is often neglected in this equation, especially in intrastellar classes, and that is this term, which is the centrifugal force term, right? So if you have a star that's rotating, if it's rotating sufficiently fast, the equator will be subject to a centrifugal force, which actually makes it less dense at the equator. And at the poles, correspondingly, the star will be more dense, right? And this term is the centrifugal force term, which allows us to quantify that value. So the first thing we did in our paper was try to rewrite this centrifugal force term to make it more easy to describe. And the way we did that was to try to express this rotation element as a dimensionless value, omega, right? So we can actually define an omega, which is a value from 0 to 1, which is defined as
the rotation rate of a star divided by the critical rotation rate, right? And the critical rotation rate, what is the critical rotation rate? It's about the velocity at which a star becomes unbound due to rotation. So if a star was rotating at this speed, the material at the equator would sort of fly off or would be marginally bound to the star. And usually this is taken to be about this much, right? So and sometimes you'll like this is a very historied calculation in itself. So a lot of times you'll see some people put like a 3/8, and there are different definitions for the critical rotation velocity. But suffice it to say that it's proportional to this GM over R cubed. And so if we write the this value omega in terms of the critical rotation rate, we now have a really nice 0 to 1 value where 0 is the star is not rotating at all, and 1 is the star is rotating at its breakup velocity, right? So what I can do now is I can actually write this omega in the hydrostatic equilibrium equation in terms of this dimensionless omega. And so I can write, you know, like it would just be, right? And if I write that into the surface gravity, the square root drops off. So we get this really neat, neat form for the hydrostatic equilibrium equation, right? And the reason why I think this is kind of neat is, first of all, I wasn't able to actually find a derivation in the literature with this particular form. And the second thing is this gravitational potential term is pretty similar actually to the centrifugal force term. It's basically a GM over R squared, right? And this is a GM over R cubed with this omega squared term in it as well, which is some number from 0 to 1. So this form actually works out quite nicely, but it's very relevant across stellar astrophysics to know the local surface gravity. One of the important reasons is if a star is rotating very quickly, there are a host of phenomena that occur on the surface of a star that are observable, and they're all dependent on the surface gravity. So one example of this is a phenomenon called gravity darkening. So when a star is rotating sufficiently fast, the certain parts of the star will glow more brightly than other parts of the star. So for instance, the equator will glow less brightly because the material is less dense there and the local surface gravity is less dense. So so it will actually be less hot, and due to black body radiation, you know, the star will actually be a little bit darker at that point. So you see an effect called gravity darkening. I think here it would be good if you can share your screen. Oh here, oh yeah. You have to stop. Oh, that's good. It's good. I got it. Yeah. So here's an actual 2-scale representation of stars rotating at different velocities omega. And so at a quarter of the breakup velocity, these stars look fairly normal. But you can start to see that they get a little bit oblate. So they're not quite spherical, they're a little bit oblate. As you get to half of a breakup velocity, you can noticeably see a dark band developing at the center, and sort of bright spots. And at 3/4 of breakup velocity, the gravity darkening effect is very obvious. And and this isn't sort of stretched in any way. This is the actual representation of the brightness on the surface of the star in a perceptually uniform color map. So it's this is actually how it would look sans color, right? Like, and the reason this happens can be described by something called the von Zipa law, which essentially I will not derive this from scratch, but I'll write it down. Essentially, what the von Zipa law says is that the temperature on a given point on the star is equal to the temperature at the pole, which is a scaling, right? Times the surface gravity to the power of some exponent beta, divided by the surface gravity at the pole times some exponent beta. So essentially, this is a scaling relation that says the temperature at any given point on this star is dependent on the local surface gravity to the power of some exponent. And usually this exponent is taken to be something close to 1/4, so something like 0.25. But this exponent beta is also very poorly understood, is a very poorly understood quantity as well. And part of this paper is to help build our understanding of gravity darkening itself as a phenomenon. So this is how stellar rotation affects stars in a sense. You have gravity darkening, and the other important quantity is oblateness, which you can define. So if you can approximate the star as an ellipse, you can define the oblateness as the semi-major axis of this ellipse. And it is also sort of trivially related to the rotation rate of the star.
Does it actually work out to be an ellipse mathematically?
That's a good question. At low rotation rates, this is also a very, very history problem, and I would refer you to there's some really, really important papers on this written by Chandrasekhar and some others. Even Newton, I think, worked on this. But in short, it does at low rotation rates approximate very well to an ellipsoid, or what's called a Maclaurin spheroid, where you have it's an ellipse on all but one axis, right? But at very high rotation rates, you have to start taking into account Roche potentials, and the density inside the star actually starts to become important as well. So it becomes very complicated at very close to the breakup velocity. But for most stars, you can assume it's a perfect ellipse.
Cool, thanks.
So so this is the actual the math. And then the last thing that I want to describe is this parameter f, which is the oblateness of the star. It's the oblateness parameter. It's defined as the equatorial radius of the star minus the polar radius divided by the equatorial radius. And it's again a number between 0 and 1, which describes how oblate the star is. A value close to 1 means that the star is very oblate, or sorry, very spherical, and a value close to 0 is that it's very oblate, right? The other way, right? Yeah, I keep messing that up. But this value f is actually trivially related to this dimensionless omega as well by this relation. And basically, if omega is close to 1, this value f will be about 0.33. That's about how close it can get to 0. And otherwise it'll be very close to 1 if the omega is low, right?
That's another way of saying the most rapidly rotating stars are about 30% larger at the equator than the pole, right?
Right. Yeah. And so what we can do is we can use the surface gravity equation that we derived, which is essentially this. This is in vector form, right? Where this is x, y, and z. And if you align the stellar rotation axis along the y-axis, the rotation, the centrifugal force term only shows up in the x and the z, right? So with this equation for stellar surface gravity, we can plug that into the von Zipa equation, and we can come up with this very long and very, but nevertheless very important equation for the temperature across the surface of a rotating star in terms of only spatial constants and or spatial numbers and this dimensionless rotation rate. So this is the temperature as a function of spatial variables. And so now that we have the temperature across the surface of the star, we can plug that into our favorite blackbody equation, like the Planck Law, to determine the intensity across the star. So I'll come to that later. But essentially, this is how we can work out, using just stellar rotation, the intensity across the surface of the star, which I show you here.
Yeah, and so
So where does this number beta come from? So you mentioned some examples of, you mentioned that it's about 1/4. Is this like empirical or?
Right. So this is also a very good question. The 1/4 number comes from von Zipel's original paper, where he assumed that stars are fully radiative. So this exponent sort of comes from the assumption that stars have fully radiative envelopes, in which case there will be a certain relation between the surface gravity and temperature of a fully radiative star. Real stars deviate from this. If you have a fully convective star, this value beta is about 0.08. So the full parameter range for this ranges between like 0.08 and 0.25. Yeah, so
I guess it would be helpful to what kind of stars are radiative.
Right. So this brings me into a segue to discuss about what stars are radiative and convective, and what stars rotate. So the basic idea behind this is that you have stars ranging from M type, which are the least massive and coolest, to O type, which are the hottest and brightest. And the M type stars tend to be convective. Stars up to the mass of our sun tend to be convective and have convective envelopes. And beyond about 6,500 Kelvin of effective temperature, there's a pretty rapid break where you have stars that beyond this point start to be radiative in their envelopes. And this is the Kraft break. It's called the Kraft break. And the importance of this can't be understated. Like, it shows up everywhere in astro, especially stellar astrophysics, where stars above this temperature are radiative throughout, so they don't have convection going on inside the stars. And as a result of this, they don't have material like plasma roiling around, and so they also lack magnetic dynamos. So stars that are hotter than this Kraft break don't have magnetic dynamos, and these magnetic dynamos are also what slows the star down and allows them to disperse their initial angular momentum to the stellar wind. So without this magnetic dynamo, in effect, this means that hotter stars keep their rotation rates for much of their lifetimes. And so you'll often see A-type stars, A, B, O stars rotating at, and even some F stars rotating at close to breakup velocities. And so observationally, you see this very, very rapid rotation increase for stars that are hotter than F-type.
And so if there are any like amateur astronomers or people who are familiar with the sky in this group, the star Altair is a well-known A-type star that actually is known to rotate so quickly that it looks like one of these, like, what is, do you happen to know Omega? 80% or something? So that's insane, right? It's rotating like 80% of its breakup velocity. Its surface profile literally looks more extreme than the right over here.
Right. And in addition, like, because a lot of the stars you can just go out and see in the night sky are brighter and hotter stars, they tend, yeah, right, because of the Malmquist bias. They tend to be A-type stars. So stars like Vega, Altair, Prasalg, all of these stars, like which you can see with your naked eye, are all rotating at close to breakup velocity as well. Yeah, so it's pretty like, we're also amateur astronomers and astrophotographers, so like these are stars we're very familiar with. They're also stars that, from an experimentalist perspective, they have the highest signal to noise ratio for any kind of measurement you can make, especially photometry, right? So you can really take exquisite like measurements of a lot of A-type stars, so that makes them valuable to study from a planetary perspective, right? Because for planets, we're looking for host stars that are very characterizable, that we can go out with telescopes and take exquisite data of, right? So a lot of these, excuse me, we care a lot about. Yeah, so now that we understand like stellar rotation a bit better, how can, like, I'm interested in how we can apply this to planets, right? So I mentioned earlier about the spin orbit angle. So how exactly is it possible? Oh yeah, go. You have a question? So?
Yes, can
Sorry, I think we can't hear you anymore.
Can see you there.
Oh, is it in the chat? Yeah, we can hear you. Try talking again. Fortunately, we can't hear you right now. Oh, you're really, really quiet.
Yeah, we could hear you at the beginning of
Yeah.
that. I don't know what happened.
Okay, sure. Yeah, so while that question is formulating, I'll just quickly say, what are the methods that exist out there to measure this spin orbit angle? So there's a couple of different ways to do this. One of the ways is stars that are rotating sometimes have star spots. This doesn't actually apply to hot stars. And the reason for that is because they're mostly radiative. And as we mentioned earlier, they don't have magnetic dynamos. And star spots are a pretty heavily magnetic property, or a convective property. Yeah, a convective property that doesn't exist for, so like A-type stars and stars that are mostly radiative typically don't have any star spots at all. But smaller stars, M-type stars that still have angular momentum from their formation often have star spots, and as they rotate, those star spots actually rotate in and out of view. You can observe this from their brightness, and especially if a planet happens to cross in front of the star spots or transit the star spots, this can actually give you like, there are ways to extract from the graph of brightness over time. There's ways to extract out the effect of the star spots and the effect of the transit and back out the spin orbit angle. Another way to do it is through astroseismology, and I am actually not too sure about the specifics of that, but Nicholas might be able to tell you more. Yeah, but I know that there's a way to do this using astroseismology. Another important method is called Doppler tomography, and I actually want to talk about this one because it's very relevant and very widely used to measure spin orbit angles. It can be done en masse. So for a star like this, it's rotating so quickly that one side of the star is actually Doppler, or the star is actually Doppler shifted, right? This is actually a major problem for exoplanet observers because one side of the star will be red shifted and one side of the star will be blue shifted, right? And so if you look at the like line profile of the spectrum of the star, if you have like an emission feature, an absorption feature, those features are actually broadened out. And the reason they're broadened out is because you have half of the star that's red shifted and half of the star that's blue shifted. So this is called Doppler broadening. And for those of you who know about exoplanets and who know about the method of radial velocity, it's a big problem because it makes it really hard to find planets around stars that are rapidly rotating. Because if you want to confirm the planets, you need to be able to look at the line profile and see if it's shifting back and forth due to the wobble of the star as the planet tugs on it, right? And you can't do that if the line is broadened to oblivion, right? So for exoplanet astronomers, historically, this has been a problem, but some people found a way to actually use it for good. And that is, while the planet is transiting the star, right? If you have like, let's imagine my cursor is a planet and it's transiting the star, right? If it starts by transiting, let's say the red side, the red shifted side,
then it moves to the side that's neutrally colored, and then it shifts to transiting the blue shifted side, right? So what you'll actually notice if you're looking at the spectrum in time domain, you'll notice that there's a little bump in the feature, right, that moves like as the planet like moves as well. So using this, you can actually, depending on how the line profile moves as the planet transits, you can actually figure out the angle between the important thing to mention here is this can only help you figure out the projected angle between the spin of the star and the angular momentum vector of the planet. And so it can't give you the total number, but it can give you the projected number, right? And this technique has been used a lot. It's the predominant technique to measure spin orbit angles.
Hold on, Yansu, did you want to jump in with your question?
Can you hear me now?
Yeah.
Oh yeah, sorry.
Right, you're good.
My Zoom always has this microphone problem. So.
Oh, that's all good.
So my first question is, so we use just like approximation formula for actually recovering the surface, the mathematical form of surface here, right?
Right.
Yeah. How can I ask how like it is valid? So it's like acceptable for like some very high resolution rotation rates.
Yeah. So which approximation were you referring to?
That's not a good sign.
Okay. I think it's about it's connecting angular velocity and the oblateness, the F.
Right. Yeah.
That's
So yeah, that's a good question. So this approximation shows up I think down here. So this oblateness factor is a definition, and it only applies as long as the star is an ellipsoid, right? Or can be modeled as an ellipsoid. And I talked to Nicholas earlier, and I said that most stars up to like the highest rotation rates, maybe beyond like 90% of breakup velocity, can be modeled fairly well with current instruments as an ellipsoid. So this is really very rarely an issue. This approximation F, right? There's this additional approximation, which is like how much is the oblateness actually? And this is itself not an easy thing, and we use this approximation right here, which is like this fairly simple approximation. But I would also say that the number of stars where we can observe observational deviations from this quantity is maybe 2 stars, like out of all the stars that we've ever observed. Really the only ways that we know of oblateness and the gravity darkening effect and the ways we can observationally constrain them are through interferometric observations. So where we're actually physically resolving the star itself with interferometry from the ground. And this is only applicable to a handful of stars that are very close to us and very bright. So the short answer here is we don't know very much about these quantities, but we know that these approximations are valid within what we know. Right.
Yeah.
Okay,
So,
yes.
oh yeah, sorry, you had another question?
Yeah, it's not actually a question, but like, okay, so can I understand this gravity darkening as a combination of like star being oblate because of rotation plus the limb darkening that we have to learn in stellar physics class?
Yeah, that's a good question. So limb darkening is actually a separate effect, and it's caused by like light scattering at the envelope of the star. It's a completely separate effect and one that we do model, but gravity darkening is specifically related to the local surface gravity of the star, which limb darkening really does not have that much to do with.
I think I might actually talk about limb darkening in a second.
So just to clarify, in the figure that you were just showing, you can see limb darkening, right, on the edges.
You can,
can,
yes.
yeah.
So we actually do show limb darkening here as well. You can notice that the edge of the star is like, it's not a homogeneous, like even for a perfectly like spherical system, it's not a homogeneous circle, right? At this point, I would encourage you to think about limb darkening as the star is not a flat disk that's just emanating light perfectly at us in all directions. There's a vector component of the light that's sort of on the limb of the star. Not all of the light is hitting your eye. Some of it is going off to the side. I know limb darkening is way more complicated than that, but yeah, I'm actually like, I think what I was going to talk about like earlier was or what I was just about to talk about is the fourth important method to measure spin orbit angle is the transit method. And I'm actually going to explain like that. This is like one of the key focuses of our paper. So I want to talk about the transit method in a little more detail. So the traditional transit model was created actually by Mandel and Agol. I think this is a 2002 paper. So like surprisingly recent actually. And this is the one that actually models the star and the planet and uses a double integral in order to, it's a pretty semi-analytic model, so it's very quick, and it actually factors in parameters like limb darkening as well, right? And so if you didn't factor in limb darkening, you would end up with a sort of trapezoidal shape. Do you have the tablet? Yeah. Yeah, so you would have like a sort of trapezoidal shape, but because of limb darkening, you have an actual a bit of a parabola at the bottom. And usually limb darkening is modeled with like a quadratic with a quadratic polynomial, and so you have like a bit of a parabola at the bottom, and then you have like your trapezoid. You want to show right, so this is the most basic transit model, right? This is, I think there was a 1995 paper that first observed a transit, and this is the model that they use. It's a very simple trapezoid. And yeah, so I could also go into derivations. I think for want of time, I won't go into the derivations in this case. But so this is the simplest transit model. The next most complicated model is where you model the star as having an ingress and an egress, and in this case, the star is perfectly flat disk, and you have a planet that's dark, that's orbiting. In this case, you have sort of like a limb that's darkened, and then the planet is passing across that. And for this case, you actually are doing a sort of double integral across the visible surface of the star's disk, right? Where you're at every moment in time, you're doing an integral over all of the visible portion of the star. And this will become important in what we're doing. The next step up from this is being able to represent an arbitrary stellar surface. So maybe the stellar surface says hello on it or something, like, or maybe it has a star spot or any combination of effects. The question is, if you have a planet that's passing in front of this star, can you model the brightness of the star as a function of time? The problem is exactly the same. You're doing the same double integral over the visible surface of the star, but you have to be able to represent this the stellar intensity, this quantity I, x and y, right? You have to be able to represent that surface. So in our paper, we actually do that again. Going back, you have to end screen sharing. You can, yeah, you can. Oh, yeah. Yeah. So in our paper, we use spherical harmonics to represent the surface of the star. And it turns out spherical harmonics are a really, really neat way to represent stellar surfaces, because there's a really, really nice way of being able to analytically integrate over the surface if you represent them or approximate them
as a low degree expansion in spherical harmonics. So essentially, what are spherical harmonics? They're a glorified polynomial, right? And if we're able to represent the star or break down the star in terms of spherical harmonics, then we're able to integrate over them. And so this a large part of our paper, I'm going to scroll down to the appendix here. A large part of this paper is essentially writing out and extending the Mandel and Agol transit model to arbitrary stellar surfaces, and specifically taking into account gravity darkening. So, this is our double integral. We're going to write that as using Green's theorem as a line integral around the edge of the star. And we're going to represent that for a star that's not spherical, but oblate. So I'll scroll through some of the heinous math and try to get to a figure. Yeah, there we go. So these are the different spherical harmonic basis elements, and the changes as a function of time during a transit. As you can see, like each part of this planet's progression across the star, and the relative change in each of these terms of the spherical harmonic expansion. And it's pretty important for the model that we produce. Like representing in spherical harmonics is especially important because you want your transit model to be fast. And the reason for that is because we have a ton of photometric data from Kepler, from K2, from TESS now. And the goal is to be able to take data for stars, right? Take transit data and like very quickly perform a fit and back out parameters of the star, right? That is the ultimate goal here. And people have not been able to do this before because even though there have been crude like numerical models of gravity darkening, they're just simply not fast enough to perform a fit, especially not an MCMC fit, right? So the advancement of this is it's like 4 orders of magnitude faster and more accurate. And this means that you can actually perform an MCMC fit. So you can take the data from the Space Telescope, you can take the transit data, you can perform a fit, and you can get like parameters like the spin orbit angle with uncertainties, right? Which is really, really crucial.
How long does it take, and how long did it take?
Yeah, so that's previous methods essentially relied on discretizing the surface of like a star into a bunch of pixels and then sort of doing the manual double integral over the entire visible surface. This used to take about 6 months on a cluster. This was as recently as like this year even. One of my future collaborators told me this, that it takes about 6 months to run a single fit. And this is a least squares fit as well. So with this new method that we developed, it reduces the computation time by greater than 4 orders of magnitude. So we can run it in about 24 hours on a laptop, and also running like a full Bayesian fit. So it's a lot faster. So basically now like fitting like transit models in order to get stellar oblateness, like both the stellar oblateness and parameters that as an exoplanet astronomer, we're interested in, like the spin orbit angle that we mentioned earlier, is very accessible. And so we actually tried to do this no problem. So we actually tried to do this on a real system. WASP 33b is known to be very oblate and very it's known, or it actually, people have overlooked the oblateness before, but we saw that there was an asymmetry in the transit. And we were like, okay, we can clearly see there's an asymmetry in the transit. It's been explained away in the literature before, but we thought that there's actually something going on here, and that something is gravity darkening. It's worth going over really quickly what one would expect to see. So again, like if you have a planet that's transiting a rapidly rotating star, you'd expect to see a perfectly symmetric transit if this planet was either transiting the the equator perfectly, or perhaps was transiting the pole directly,
which is
right?
unusual. We wouldn't expect to see like a perfect pole on orbit, but it's quite, if stars or planets have low spin orbit angle because of their formation process, it could quite be possible that it transits perfectly equatorially, right?
Right.
So in those cases, you'd have a perfect symmetrical transit.
So essentially, you can see really wacky transit shapes if you have a planet that's not aligned with the star.
You can imagine if yeah, the transit core was like this, you would have like initially it would block a lot of light because it's transiting a bright part of the star. Then as it transits the dimmer part of the star, the graph of brightness over time would actually go up. And then as it transits the light part again, it would go back down. And then so you have like a W-shaped transit, which is really wacky, anomalous. And so, then you can end up with asymmetric transits if you have like the star is not going to be like edge on always, right? It's going to be like orbiting, like there's probably some like polar angle, and then like now if you have a chord that's asymmetric as well, now you will have like a very wacky looking asymmetric transit.
So the goal of this entire method is essentially to do the reverse problem, to be able to tell from the photometry or from observing a transit what the spin orbit angle of the system, of the planet system is.
Yeah, so we actually decided to apply this on WASP-33b, which is known to have a planet, but it was not known to be. We knew that it was a very hot star, like an A-type star, and so that means that it's likely very rapidly rotating. But people actually hand-waved in the literature. They hand-waved away the fact that there was an asymmetry in the transit and ascribed it to various effects that we were not convinced was actually the case. We believe that it was the asymmetry, and when we fit it, you can see like the traditional spherical model is in blue. This is like a symmetric transit, but you can actually note the red model that we like developed in this is the oblate star model, and it is markedly asymmetric, and you can see this really clearly in the residuals. The oblate model very clearly fits the profile, but the spherical model like definitely does not. There's like a real problem with the spherical model. Right. And it's nice to be able to get like literally the exact shape represented by this and explain WASP-33b's transit asymmetry from the perspective of stellar oblateness. So now that we've modeled this, the important thing is, can we back out the parameters? Can we back out the parameter of the spin orbit angle? And the answer is mostly yes. So this is like a bunch of samples from our parameter space of the MCMC fit, right? And we've actually like shown them transiting the surface of WASP-33, the star, right? And as it turns out, there's a degeneracy. Like it's impossible to know, like it would produce the same light curve that's transiting this way or transiting this way. But there is actually a way to break the degeneracy using Doppler tomography, right? One way to break the degeneracy is that there's prior Doppler tomographic data of WASP-33. And this is actually why we picked it, because there have been multiple methods to independently measure the spin orbit angle. So we can compare our measurement of the spin orbit angle to those other measurements of the spin orbit angle and figure out whether they agree or not. Doppler tomography actually helps us break the degeneracy, right? And there's also there's dynamical constraints. The fact that the star is oblate creates like a gravitational like quadrupole moment, right? That actually causes a precession of the orbit over time. And from that precession, if you observe the system over a very long period of time, which people have been doing, you can actually notice that the transit shape is changing over time. And from that, people have made dynamical constraints of the oblateness as well, and the spin orbit angle. And the numbers that we produce actually correspond quite well to the independent measurements of the projected spin orbit angle. But it's important to note that this method actually gives you a true spin orbit angle. It's I think one of the first methods that actually gives you a true spin orbit angle, which is very, very useful. And so since there aren't other methods to measure the true spin orbit angle, it's hard to corroborate the true spin orbit angle, but it corresponds well with the projected angle, which is very important to note. So yeah. So WASP-33 is a pretty important system, and
So this is our test case.
Mhm.
But I think this method in general is just a really interesting go-between whenever you have cases where you have photometry and you want to understand a physical system that maybe is oblate, maybe has a star that's rotating, or even if you have like a star with any surface features that you want to be able to model, spherical harmonics, and this method that we've coded into this code package Starry is a really useful way to be able to understand the photometry better and model it. Yeah.
Thanks. Do you think we should expect a catalog of spin orbit angles in the future?
Yeah. So
that is what we are working on.
That's what we're working on. So yeah, basically the researcher that said that it would take 6 months for his fits decided to abandon his method and collaborate with us. So we're working on that for the next.
The nice thing is, especially the test spacecraft is scanning the entire sky. It's found a real treasure trove of these, like, because there's a Malmquist bias, right? A lot of the bright stars we see in our night sky are actually like A-type stars or O-type stars or B-type stars, right? Many of the planets the TESS is discovering are around these really hot stars. And so that actually provides this really, really large experimental data set for us to probe this. There's also a bias in terms of hot Jupiters are easier to detect because they result in really deep transits and really high signal to noise ratio transits as well. So TESS is really perfect for this. And so this is going to be a nice like thing that we can do statistically in order to answer one or the other hypothesis very soon, right?
Thanks.
I have one more question.
Sure.
So if there is a star spot, does it help? I don't know, but like I was just wondering how much improvement it will give to practice degeneracy if there is a star spot on the surface, because we have we can determine the rotation speed based on the oblateness, etc. We know, like we have non-zero information about how some star spots will move, right? So
yeah, that's a good question. The first caveat here is because these stars again are usually A-type stars that are rotating very quickly, they tend not to have star spots because star spots are an effect of convection, which these stars don't have. So we very, very rarely, if ever, see star spots on these kinds of stars, which means we can't use them. That being said, people do use star spots on slowly rotating stars. And if you can see star spots, you can occasionally constrain the spin orbit angle using similar methods to this, right? Although this code that we've written actually could help doing that as well.
The general code package Starry that we've we've developed with like gravity darkening in this paper actually is used to model star spot rotation as well. And like there's a lot of like literature about how you can go about doing that. But it's actually like an important way to measure spin orbit angle as well.
Yeah, but the other thing is we do know how fast these stars are rotating. At least we know the projected rotational velocities. And the way we know that is through spectra. We can measure the spectra. We can look at how broadened the spectral lines are. And so we can measure what's called V sin I, which is the projected equatorial velocity of the star. And so, for instance, with that information, we can tell that if this star, WASP-33, were perfectly pole on, it would have an omega or like a rotational velocity relative to the breakup velocity of about 0.2 or 20%. Yeah.
There are other stars as well that are like that have such high V sin I's that if they were pole on, like since it's a projected equatorial velocity, they would be rotating faster than the breakup velocity. So V sin I alone can help you make constraints, and is very useful to be used in tandem. Like this whole approach is mainly about taking everything we know about the star, right, and throwing it at the wall to see if we can understand more about the planet.
Right.
And yeah, Doppler tomography and V sin I are all important ways to do that. Right.
Okay. Yeah. Interesting.
Anyone have any other questions?
Yeah. Go ahead.
Yeah, Kyle. I don't think we can hear you.
Yeah.
Oops. Yeah.
Sure.
I wish we could come down to Pasadena and give a talk.
Yeah, hopefully one day.
Yeah. Sure. Is there anyone else that tend to Aspen, by the way, Nicholas, here?
I couldn't convince anyone else to go.
Well,
Have you,
Wow,
do you guys attend any AAS sessions?
oh, AAS was
AAS
fully
canceled,
canceled,
yeah.
right? So
Right, but I thought there were like sort of like these like affiliated sections.
they
Maybe
haven't started yet. So they would start on Tuesday. Yes. Okay.
Okay, Kyle has, I'll just read the question out loud. So he says, you've tested this with WASP-33b as a good test case to prove this method works. Have you tested it with stars that have a small omega to show you get the expected results?
Yeah.
Yeah. So actually, WASP-33 itself has a fairly small omega of 0.2, right? For as far as A-type stars go, that's quite small.
We've compared it to the traditional Mandan and Agol model. So like the model that's used to model spherical stars, and it agrees really well, or in the low omega approximation, it is the Mandel and Agol model.
Right. It would just
So yeah, it's the same as the Mandel and Agol model for low omega, and so we've confirmed that's the case. But I guess yeah, we could also compare it to like a low omega star. It would be effectively the same thing.
Yeah, the exciting thing about this code that we've written to be able to model oblate stars with gravity darkening is that it's applicable to more than just modeling planet transits. The reason why I asked about Aspen is I know a lot of people in Aspen were talking about the recent discoveries of stellar mass black holes and stuff. I know a lot of the discoveries of stellar mass black holes are predicated on sort of finding a star that's sort of varying in brightness for unknown reasons. And usually that's due to something called ellipsoidal variability. And ellipsoidal variability is actually an extension of gravity darkening where you have tidal distortion due to a compact object. And the tidal distortion is changing the local surface gravity of the star, causing gravity darkening, and thereby like resulting in an observed variation in brightness of the star. This is something that can be modeled if you're willing to make certain simplifying approximations using our code package starry. So I think it would be really useful for people to go out and use this code for binary stars, maybe modeling stellar mass black hole binaries and stuff as well, and see if it might be useful for them to model these in greater detail.
Yeah.
Kyle, do you still have a question?
Yeah, and also that sounds good. So I missed the first day of Aspen, but they actually surprisingly talked not very much about finding black holes in binaries in this form. But you also made an interesting point, which I just want to clarify. Also, Kyle has a question, but let me just interject. So I think it's easy to look at this paper and think that it's sort of like trying to probe an exception and that most times, this isn't going to apply. But am I right in saying that this is actually more like the rule? Like if you really want to describe these stars, this is going to apply to most A-type stars? Or
It's actually, we actually don't know. And this is actually one of the big reasons we want to try and do this en masse, because there's been one, this actually relates to Kyle's question. Do you have a higher omega star in mind to test this on? Yes, there's actually a star called Kelt 9b that's well known to be extremely oblate and present a marked asymmetry in the transit. And we did test it on Kelt 9b as well and got very agreeable results. But like, we know that the effect, typically our SNR hasn't been high enough in the past to be able to look at a transit and just visually say, well, that's asymmetric, right? So even in the more extreme cases, the effect is going to be subtle, like you can see here. But there's another reason. I think I want to interject and say, like, the most of the planets that we've discovered so far were discovered with the Kepler Space Telescope, which was exclusively looking at, you know, G-type stars and less massive stars, which tend to rotate much more slowly. And these do make up a large number of stars. Like, these are the majority of stars. Majority of stars are M-type and very slowly rotating, but the majority of bright stars is a very different story. And the TESS mission is looking at a more representative sample of bright stars, right? And amongst those stars, rapid rotation is more of the rule and not the exception. Yeah. And so the crucial thing would be to apply this method en masse, and we can actually see, like, there are ways to also, like, compare to other models to see, like, or like, does rapid, like, stellar rotation represent the reality in most of these cases? You can also just look at the MCMC and see, oh, like are most A-type stars consistent with, like, with rotation, or are they, like, are most A-type stars, like, readily modelable as a sphere? This is actually something that's not well understood, I would say. Yeah. Mm-hmm. Also, from, like, you can say from what we might expect. One of the enigmas has been that you expect a lot of A-type stars to be rotating rapidly enough for this to be a significant influence, but they haven't been modeled this way in the past. So so I would personally expect that, yes, a large proportion of these systems should be amenable to this method. Yeah.
Some any other questions? So we're already a little over time, but you know, it's up to the twins' discretion whether.
Oh, yeah, I have
Okay.
time.
Answer
I
others.
set up this meeting to last till 6, so you guys can keep asking questions. No questions, it seems.
Yeah, I think.
Mhm.
Yeah, I think there are no more questions. So let's thank our speakers, and thanks very much, everyone, for coming. So just as some logistical points, like the future is a little bit uncertain because it's not so clear whether or not we can have in-person journal clubs anytime soon, or whether that would be a good idea. But tentatively, we have scheduled Sarah Habib 2 weeks from now. So she was supposed to go today, but because of this Omicron thing, we delayed it 2 weeks. And so that's what the tentative plan will be, an in-person talk at that time, but it's very possible that it needs to be delayed again. So those are just the rough logistics. So just keep an eye on your inbox for the details. All right. Thanks so much.
Yeah, thank you all for coming. Thank you.
Thanks for the talk.
Yeah.
And you can stop recording if you'd like.